just messed up the wires. It never works. We have so much trouble with connecting everything. Ja, nou dat is één, maar ik heb ook gehad met de sprekers, dat gewoon die microfoon een beetje dicht op elkaar gaat. Ja, nee, maar dat was het probleem? Nee, dat was het niet. Wanneer was dat? Nee, daar was ik bij. Daar was ik bij. Toen hebben we een beetje
op een gegeven moment overgegaan.
Nee, maar toen hebben we weer teruggezet. Toen hebben we even verbogen bij een stukje van zijn licht afgehaald en toen was het over. Maar we moeten maar even een test draaien, dat is goed. Ja, weet je, ja, maar daarom had ik ook de hoop dat we inderdaad iets van standaard of zo hadden. Ja. Maar ik zou ook, ja, het moet wel opgenomen worden, dus anders we hebben wel echt iets van audio nodig.
Ja, zeker.
Ja. Ja.
Ik zei net al tegen Casper, hebben we ook iets anders dan een groenscherm?
Ja, ik heb het op zijn laptop staan, maar hij is er aan het eten. Als hij klaar is, dan zet ik het aan. Ja. Ik heb... dus inderdaad wel heel...
groen. Het is heel groen.
Anders dan kan even als Casper zijn laptop ook even aan. Zullen we anders even jouw laptop even aandoen, dat we even beeld aan kunnen zetten?
Is goed?
Je hebt hem erachter liggen, neem ik aan, toch? Ja. Je hebt hem erachter liggen, toch? Nee, waarom? Let me figure this out. How hard can it be? Famous last words. Let's see. And how one headset, one, two. Test. Ja. Hi. We're going to start in about 5 minutes because of the high traffic still. Some people are coming in, so 5 minutes, people. Test. Test, test. Hallo. Hi. If everyone would want to come to the front, sit here, please. Then you will be able to see it much better than where you're sitting right now, for the people in the back. Thank you. And also it will not look so empty. I feel so alone here. Yeah, you can put it directly on the second one, actually on the second slide. Oh, yeah. Shall I do it? I'll do it, yeah. Yeah, that's fine. I will just press the buttons. Oh, this works also. Oh, great, thank you. Yeah. No, I have my hands full. I will just push the arrow buttons. Yeah, I'm gonna start. Well, welcome everyone. I know that not everyone is in yet, so maybe we will see some people later. I know it's super busy with traffic today. So I'm actually very happy to welcome you here today on this International Women's Day. So yeah, it's a special day. I am Martin van Es. I am a front-end developer at Codestar. Codestar works with big and fast data, and it's also what the talks are going to be about today. We want to do data and combine with functional reactive programming and the backend and the front end. Today we're going to have the first talk is going to be about Apache Spark from Marcin Siemaniuk over there, and after that we're going to have a short break. You also have the opportunity, of course, to ask your questions, and then is the time for the second talk by Caspar, who is our own colleague. So you can, if you want to tweet, you can use the hashtag Codestar Night, and if you have any questions, just ask the colleagues with the same polo shirt that I'm wearing. So, yeah, I want to direct your attention to a couple of other volunteer groups that we that have asked for it. Joy of Coding, if you might know it, is coming up, and yeah, they have plenty of great speakers, of course, again. And the second one is Girl Code. They are a meetup group who are also just volunteers who want to close the gender gap in programming. So the first talk is going to be by Marcin, and Marcin is a developer at Tantus Data in Warsaw, and he has been consulting in well, Apple, Spotify, and Telia in the past, and his talk is going to be about Apache Spark. So give it up for Marcin.
Hello? Yes. Would you like to learn what Spark is good at? How does it work under the hood? What kind of pitfalls you can face? By the end of this talk, you'll have understanding of how it works under the hood, how to fix common problems, but also you will get an overview of common use cases, so you will know what you can use it for and whether you would like to start working with Spark or not. My name is Marcin. I work at Tantus Data. At Tantus Data, we do everything related to data, basically. So from cluster installations through data application development, training, supporting of teams of data engineers and data scientists. And myself, I've been doing all of this, but on a daily basis, I act as an architect and developer. First, I'll introduce to what Spark is, and then we will have an overview of use cases. Some of them will be on a high level, some of them will be a little bit more detailed, so you get the understanding. And then we'll have a deep dive into how it works under the hood. So I'll show you a few problematic cases and how understanding of how Spark works will help to solve them. And at the end, I would like to show a little bit of a big picture. So big picture from the technology point of view, but also from the point of view of organization and processes. So I'll share my lessons learned. I'll share my conclusions from working in data projects in the past. So let's get started. Spark is a general engine for distributed data processing. So you can express your business logic in one of these languages, and it will take care of distributing the load. It will take care of spreading the load into multiple machines, so you can process your data faster, you can process larger data sets. It has a streaming API. It has a machine learning library, but for today, we're just going to focus on the core of Spark. And let's get started with some use cases I've worked on. And let's simplify it a bit. So mobile app company, we have a mobile app which connects to backend and then writes the data to a database, let's say SQL database. And what you would like to do is you would like to improve your app. You would like to improve your app by knowing how the customers behave. So you decided to store the events. What kind of events? That the user clicks a button, scroll through the screen, maybe look at a certain view in your app, and then you can connect your analysts to the database, and then they can have a look if the user, why the user have not become premium, because he went to the go to premium page by mistake and just immediately clicked the button, or maybe he was trying to, but the flow was too complex for him, or maybe the application has just crashed. And so far, so good. Your application grows, you have more analysts, they're trying to run more complex queries, maybe some machine learning. But at some point you are so successful that you have to solve some technical problems. So the number of events you've collected is huge. You are overloaded with number of requests coming to the database, and your analysts simply cannot do much with it anymore because they cannot run any query. It just runs forever or just crash. Unfortunately, it is quite well-known problem, and a solution I would like to propose is that instead of storing the events to a database, you can store it to HDFS. So if you are not familiar with it, it's a distributed file system like Linux one, but HDFS takes care of splitting large files and saving it into multiple machines. So you get scalability, replication, stuff like that for free. And then what you could do, you could expose your analyst to the Spark API. So Spark will take care of distributing the business logic they've expressed, reading the data from HDFS and returning the result or writing the result back to HDFS. And this is just to give you what Spark API looks like, just to give you an idea. And I want to emphasize on this group by, max, average, join, select. So you're familiar with SQL, so you can get the idea what this piece of code does. And the point is, it's quite simple to express the business logic if you know SQL. You also get an API which is a little bit lower level, like if you prefer to do functional programming. But the point is, it is quite simple to express the business logic and do all kind of general use cases any company has. So doing ETL, so reading data from multiple places, doing some cleanup and transformations, and writing it to some common place, or calculating KPIs, so you understand how the company is doing with acquisition, how it's doing with revenue, and tons of other use cases, A/B tests, running them and then analyzing the results, anonymization. GDPR is coming, so it's likely that you have to do some anonymization on your data, calculating fraud, churn, running machine learning on top of that. But enough of general use cases. Let's have a look at something a little bit more complex and more concrete. Examples from telcos I was working on. And let's get started with network improvement. So telco network is a set of base stations, and customer travels around, they get reconnected, and they get various experience, depend on the characteristic of the base station, depends on how crowded it is. And what you would like to do, you would like to improve your network, so you would like to invest some money into upgrade of the base stations, but you would like to make it smart. Your budget is limited, and what you would like to achieve by the end of the day to provide better network for as many customers as possible, so they are happier, they are more likely to stay with you. And if you think how to do that, you would, first of all, you would have to analyze the historical probes you have from the network. So what was the customer's throughput, what was the customer's latency, and you would have to come up with a score for the network quality for each customer. Then, based on the score, you would have to come up with a churn model, so you understand how the network quality affects customer churn. Then you can simulate the actual network upgrade. So you know the characteristic of the new base station, so you can calculate what would be the network improvement for each of your customers. You have the new score, and then if you mix those two, if you mix the new simulated score with the churn prediction model, you get an idea how a network upgrade affects the probability of your customer to leave you, so the actual business value. And just 4 points, but you can imagine this is extremely hard problem in terms of the calculations you have to do, in terms of how many iterations and how smart you have the model should be. And I would say start with something simple, with linear model, and play around with it. But these kind of problems are definitely worth doing if you think about the money you invest into the network. You want those investments to be smart, and also the value you can get out of it. In companies like telcos, like large companies, any percentage change in the churn stats is a huge win. Very quickly, one more example, so social network analysis. So a lot of companies do that because social networks are highly predictive, and in telco you can do that by simply connecting your customers based on the call they make, based on the text messages that they send, and narrow it down to close friends and family groups. And then if you mix that data with historical purchases they've made, you can try to find the people you would like to target. You can try to find people who would be influencers, which means giving them an offer, giving them a good offer with brand new phone and new contract might just spread out. But this kind of problems has been there for a very long time. People have been doing that. So why do I propose to use Spark for this? The traditional way of doing this is that you get the data, you get it to some R server, or maybe the analysts take it locally, and they play around with the data, but usually the data volume is too large to just take it to one machine, so you have to either play around with some aggregates or just some samples. And then you might end up with this very well-known blind man and elephant problem. So when the blind man is touching part of an elephant, they get completely different ideas about what an elephant is. And exactly the same could happen to your data. But if you are working with a system like Spark instead, you define your business logic, but the actual processing is somehow closer to the data. So you just send the send the calculation, the analysis to the data, and you can work on the whole data set. So you can analyze all the data, you can do the analysis faster, so you can have faster feedback loop, you can iterate faster. Also, you don't have any extra data copies in this case, which might be quite important when you think about the upcoming GDPR. And problems which I've described, like analyzing graphs of social interactions and stuff like that, they are mostly implemented somewhere, which on Spark, which doesn't mean you can just take it out of the box. You would have to change some parameters and apply it to your problem, but it doesn't mean you have to start it from scratch. Last example of Spark use case I was working on would be analyzing geospatial data. So imagine that you would like to build a map, either general map service like Google Maps, or you are building self-driving cars and you need a map you can trust, a map which is crafted to your use case. And if you build such a map, you probably have to rely on really many data sources. So maybe you have the car which takes a picture and you blend it with artificial intelligence. You most likely have tons of editors who are looking at satellite data and customer reports and bug reports, and they draw a map and fix the bugs on the existing one. Maybe in some countries you don't want to invest yet, so you buy some data from vendors, and maybe you would like to look at open source geospatial data repositories as well, and blend that data together in order to get a new version of your map, better version of your map. And that means you have to get a lot of data, you have to do it quite often, you want to iterate fast. And just to give you an idea of what kind of operations you would have to do, you would have to get data from, like the road data from multiple sources and make sure there is no hole in the data. You would like to get information about like newly opened coffee house, or maybe you would like to update the pickup point for a given address because customers are complaining about that. And the whole point is data from many vendors, a lot of operations. Some of the operations are extremely expensive in terms of CPU time, and Spark gives you an easy way to distribute that data and get the many CPUs you need. So if you look at the map, in order to distribute processing of the data for a map, you just need to come up with a way to split the data into sectors. This is, of course, a little bit too simplified. Probably you want to control it better. But the point is each sector will be processed in different JVM in different machines. You get many CPUs. You process that data faster. You iterate faster. So a quick summary of the use cases. You want to use Spark if you are processing large data sets, or if your computation is extremely expensive in terms of CPU, then Spark gives you a reasonably easy way to distribute it. It gives you SQL-like interface, so analyst-friendly, but also if you have more complex problems or you prefer functional programming, it gives you such an API as well. And now I would like to do a deep dive review. So deep dive into how Spark executes the program, how the partitioning of the data works, how the caching works. And why do I want to do it? I want you to have a bit better disaster recovery plan than this. And why am I talking about disaster recovery plans? Because from what I saw when working with clients, it is easy to implement a Spark program to express the business knowledge. Even if you test it like locally, it works. But then you go to a cluster, it fails, and you don't really know why. It's not obvious because Spark hides a lot of complexities from you. But if you are handling large data sets, it's likely that you will end up in some edge cases. So let's get started. First of all, you need to understand that when you work with Spark, you work with either RDD or data frame, and it looks like you're working with a local collection, but the collection is not local at all. It is split into multiple partitions, which are likely on different machines. And then Spark can do two types of transformations. First of all, the simple ones, which work on one and only one partition. Spark does not have to exchange data between partitions. So if you do a 2 uppercase for each record in your data set, if you do 2 uppercase for each record in your data set, you don't really need to exchange the data between partitions. You just do it in place. And Spark uses that knowledge, and it pipelines these kind of operations. So if you do 2 uppercase and then reverse on a string and so on, these kind of operations can be pipelined, and they form a task. So they are done in place. Task is the simplest, the most granular execution unit in Spark. And one partition means one task. But, of course, you would like to express something more complex. You would like to do join of your data or group by key and stuff like that. So in order to do that, Spark has to pull the data from multiple places into one. So user ID 1 goes to one partition, user ID 2 goes to another one, and user ID 3 goes somewhere else. And it doesn't necessarily have to look like that. This is something you don't explicitly control because it's just a hashing algorithm, so we might end up with something like this. Although you can control how many partitions there will be in the output. So it might be like this, or like this, more or less. So from 10,000 feet, Spark application looks like the following. As an input, you have a partitioned data set, and then Spark tries to apply as many simple operations as possible. So they work on one and only one partition. But at some point, you do, let's say, join, and Spark has to shuffle the data over the network. And then it tries to do simple operations again, and then you shuffle the data again, because maybe you're doing group by key. So the shuffle is something which is expensive, a lot of I/O is involved, and also a lot of things which can go wrong, and we will be looking at it in details. And let's get started with the simplest scenario ever. Let's say you are reading some data set from HDFS, and this data set has a timestamp column. And out of that, you would like to calculate information about a year, a month, and a day when given event happened. And Spark will pipeline all these operations because they are simple. Nothing really can go wrong. It just reads a record and calculates a year, month, a day out of it. And then maybe you would like to store the result to HDFS. And this will be one task. So Spark will read one block from HDFS, pipeline all the operations you requested it to, and it will write a new file to HDFS. How many of such tasks you will have? Let's assume you have 1 terabyte of data in 1,000 files, and each file is 8 blocks, means 8,000 blocks, 8,000 tasks. Each task will do exactly the same. The only difference is it will be reading different portion of your data, different blocks from HDFS. And each task gets run on an executor. Executor is a JVM somewhere in your cluster. When you start your Spark job, you control how many executors you want to give it, how many CPU cores you would like to give it, and how much memory. So let's look at something more complex. Imagine you would like to join events dataset, quite large, with some small dataset of users. And let's imagine our events are uniformly distributed between users. So there are roughly the same number of events with the same user ID. So what will happen is Spark, again, will read one block from HDFS, and then it will organize the events data based on user ID. It will write some portion of the user's ID to bucket 1, to local disk, some portion of the users to the bucket 2. And the rule is that if 2 events are for the same user ID, they go to the same bucket. All the other tasks for events and for users will do exactly the same. And then Spark will create another set of tasks. Those tasks will be performing the actual join. So they will be pulling the data over the network, the data belonging to the same user ID. So this task is performing part of the join for bucket 1, then for bucket 2, and so on. So how many of these tasks will have? The default is controlled, this is controlled by a single parameter, and the default is 200. And what does that mean for us? 10 terabytes of events multiplied by 200 tasks is 50 gigs. So each of these tasks performing part of the join will have to handle 50 gigabytes of data. It's a JVM. You probably don't want to be your JVM to be this large for just performing a join. And it doesn't necessarily mean it will fail, because Spark can spill the data to disk, but that still degrades your performance. But also it's likely that you'll see something like this: garbage collection problem, out of memory problems, or any problem which at first glance it won't really look related to what you're doing, but you have to deal with them. So first of all, you have to understand the problem. You have to understand where it's coming from, what the size of your data is, and how many partitions you should have instead, how many tasks you should have instead. But once you understand that, solution for this problem is quite simple. Just increase the level of parallelism. So this is how you do that, depend on which API you are using. So let's have a look at something trickier. A skew join. So we have 10 terabytes of events, but then one user ID has many more events than the other ones. So one user ID has 1 terabyte of events, and you would like to join the data and just save it to disk. Nothing complex. So you would like to join the events with user to just add some extra information. What will happen is exactly the same, let's say, query plan. But the problem is one of these tasks will have to process 1 terabyte of data, because how Spark implements it is it pulls all the events, all the user IDs, because you are joining based on user ID. It pulls all the events with this user ID to the same machine, and this will crash for sure. So what do you do with this? First of all, you have to understand where this queue is coming from, because it is likely that you have a problem with your data. Maybe your data delivery mechanism is broken, and you end up with user events with user ID null, and you have to fix that first, because otherwise the analysis doesn't make much sense. Then maybe it's a wrong logic, so you calculate your data frame in multiple steps, and at some point you introduce a bug, and you end up with null or something, some dummy value, which again doesn't make sense, so you have to fix that first. But if it's just okay, if your data looks like that and you still would like to perform the join, this is a quite simple technique. So here we have user ID 1, which is the problematic one. We have many of them, and we want to process them in multiple tasks. So what we can do is we can provide a salt column. So we are introducing some randomness to the events. I have randomly generated the users from 1 to the salt from 1 to 3, and this is just random value. Then user IDs we would have to duplicate. So user IDs, we create a user ID with each possible salt. So we have 3 times more users. And then, if we perform the join, we perform the join not only based on user ID, but also based on salt. So one task will process this users. This task will process just one, and this task will process again part of your data. So a quick recap of SKU join. Know your data, understand where the salt is coming from, but if it is something you still want to do, you still want to do this SKU join, add a salt. This is a very simple technique. You just have to be careful about the logic. You just have to make sure that adding the salt does not change your logic, but this is a good starting point. And last technical part for a deep dive I would like you to understand is caching. So first of all, why do we need to cache the data in Spark? The reason is transformations are lazily evaluated, so they are evaluated once they need it, once you want to materialize the data. But that also means the partial result never gets stored to disk. So if you want to reuse some of your logic, and if you want to, let's say here, RDD1 is calculated out of the blue transformations, and then you would like to do some extra transformations on top of that and write the result to disk, and then you would like to do something similar once again, the blue transformations will happen twice. And to give you an overview what that means for the case of PageRank algorithm, the core of PageRank is that you have to do join of 2 datasets, links and ranking, multiple times. You do it in iterations. So first you do a join and you calculate new ranks. Then you do the join with the new ranks again, and so on. That means you have to read that data from disk multiple times, unless you use caching. If you use caching, the links will get stored to memory once they get read from disk for the first time, and then you will reuse the data from memory. So in order to do the caching well, first of all, you need to spot which data to cache, and the candidates for caching is any place where you reuse the objects you are working with, the data frames or RDDs. Then, in order to do it smart, you have to understand the size of your data and how expensive they are in the calculation. And you have to know that because you cannot really pin an RDD to memory. You cannot set priorities, just LRU algorithm. So caching second data set might mean you lose the first one, So you have to be smart about it. You have to know what's important to cache, what is expensive to calculate, so you can reuse that. There are tons of other gotchas we don't really have time for, but I would be happy to discuss them later on. And really, the whole point is that you need to understand the data, and you need to understand how it works under the hood in order to write performant Spark programs. And now I would like to do a little bit of bigger picture. So this is what I show you in the beginning for the mobile app company, but it's likely that you will want to read the data from multiple sources and write the data from to multiple locations. And maybe you'd like to use Druid or maybe Elasticsearch if you want to do dashboards. And if you Google for that, you can very easily find a code which connects to all of these systems, and it's not a problem at all to write it. But I would say be careful about what you introduce to your ecosystem. Make sure you not overcomplicate things. Make sure the things which you are introducing to your system make sense. And also make sure you understand the basic characteristics of those things. Because if you are connecting to Postgres, well, you can very easily distribute Spark processing, but if your main data source is Postgres, it just won't work. So understand the systems you are working with. And this is the big data landscape. You need like lifetime to understand all of them, so be smart. And you came here, which means you are interested in data. These are a bunch of challenges which probably you will have ahead, and they are not necessarily Spark related, but you will have to come up with file formats you would like to use, how to deal with data evolution so you don't get stuck with some schema, how to build pipelines, how to monitor them, and how to monitor the data itself, how to organize machine learning models so you keep track of them and you understand what is built of what and how to use the output and which one is the good output right now, and so on. So because of that, I would say you should come up with some common tools and knowledge you are sharing, and you should do that from day one, because like if you, just to give you an example, like analysts is not very much interested in JVM problems and in garbage collection, and he should not be. But on the other hand, you should expose them to most common problems they might face and how to write performance queries, so they can do it on their own and they are not blocked by just the fact there is some simple problem and which they don't understand because they just rely on the SQL interface. If you know a little bit more about, if all the people who are working with the systems in your infrastructure are familiar with most common problems, it really helps to all of you. And last picture I would like to show you is the hierarchy of needs in the data science. So deep learning and machine learning, this is something everyone wants to do. And sure, you can go back, you can just manually pull some data and do some dirty POC real quick. But if you are serious about that, if you want to make sure you can benefit from that on daily basis and you can improve your product continuously, you need to make sure you can rely on the data delivery mechanism is reliable, you have monitorings on top of that, and so on. And this is, again, something to start with from day one. So the conclusions, the top 3 conclusions are Spark can help you with distributing the load, with crunching a lot of data, but you should know how it works. That really helps if you want to build performant programs. And the big picture, the whole infrastructure, think about it from day one, think about the direction you are going to. And yeah. Yeah, I will be happy to answer your questions now. And also, if you follow me on Twitter, I plan to do a write-up and describe a little bit more details about what I've been talking about. And also, I'll write a summary of the questions I will get either now or maybe during the, yeah, maybe later, yeah.
1 second, please. 1 second. Here we go. Because otherwise we cannot record it.
Thank you very much. I have several things, but really short. You spoke 2 times about the functional paradigms in Sparks. I would like to know if it's best practice to use a Scala or also Rix Java is possible as a way to interact with the functional paradigm in Spark. The second thing is related to the problems with the cache, with the garbage collector. Actually, for the garbage collection, I would like to ask you if it's like the normal Java, that you are completely, basically independent by the framework, or you can allocate in Spark the heap for each executor so that you can kind of having an architectural strategy for the garbage collection. And most important, testing. We didn't speak about testing. To prevent problem like in the skewed join, for instance, where you have all these problems, what you do as a testing strategy, you do test-driven development, you do some mocks, you do some Monte Carlo simulation, you do some integration testing, because I think it could be central to this. Thank you.
Okay. So let's start with...
These were 3 questions, right?
Yes.
Yeah, okay. So the first one.
Yeah. The last one, because that one I remember.
Like it.
So testing, definitely test your code, and problems like skewed join is really hard to test. So it's more coming with you understanding the characteristics, the data stats you're running, and the only thing you can really test locally is the fact that the way you solve the skewed join problem does not really break your logic. But testing, generally speaking, testing, doing TDD or all kind of approach you would like to do, it's definitely something you should do, because it makes you iterate faster. If you have your logic implemented and then you go to a cluster and something breaks, it is just much slower to figure out what was that, and it is much slower to iterate. So, and it is even slower than with with general, like if you build web app, you get the feedback loop much faster. But with Spark, it might be that you want to crunch a data set, you leave it for like half a day, and then you get a bad result, and then what do you do? Then you have to figure out where it is, so test as much as you can locally, and it is quite easy to test the business logic, at least locally. Spark can be run in local mode, and no problem with that. The other two help me.
Oh, I would say 1 second. I would maybe give the choice also to other people, and maybe you can discuss it during the break. Good. Is there someone else who has a question? If nobody has a question,
we can discuss it later.
We have some reserve questions, so it will be good. No one? Yeah, you have a question?
Yeah, sure. Hey, so a few points that you touched upon said that you really need to understand your data. That's a valuable thing in doing Spark development. Do you have some tips on how to actually get that knowledge about your data? I mean, you can figure stuff out when stuff is running.
Mm-hmm.
You can see stuff in your Spark UI, but that may be too late.
Yes.
Do you have some pointers there?
So Spark UI, well, it tells you something about like what went wrong, but if something went wrong, it's already quite late. But it is quite often that Spark UI gives you an overview of that something went wrong, but it doesn't really tell you anything about, let's say, your key distribution. So I would say when you write your program, first of all, you can go to, let's say, Spark Shell and do some interactive analysis of the data you are running. And if you expect that, if you are not sure about the data which will come in the future, it might make sense to use accumulators. So Spark can accumulate some stats about the data and output it somewhere. So at least when you run the program and something went wrong, it can give you some idea of what was that. It makes your code a little bit clumsy. And if you do any extra stats, it's something. Well, it also affects the performance, so we need to find a balance, and well, it depends on the situation. But if you are touching a data set for the first time, it definitely helps if you go to some interactive programming with the data, so you get some stats, you see what it looks like.
Other questions at the moment? Yes.
So you talked about use cases for Spark and problems with partitioning, but sometimes there's a more fundamental problem. So everything you do in Spark is still like map reduce, right?
Right.
And so I'd like to know, have you come across examples, maybe in your work with Spark, where you just had to admit like, okay, this cannot be done in map reduce, or do you have like suggestions for workflows which might be difficult at all to code in MapReduce style?
So I have not come with an example as such, but an example of thing which some people are struggling a lot, is that you cannot really control what is going on with each executor and inside each task. So, for instance, some people are complaining that they cannot instantiate an object based on per executor. You can do that per task, but it's much harder to do per executor. So this kind of stuff. So it's useful. The examples they were talking about, I've heard, is about logging systems, which needs to be instantiated just once per your JVM. But I would say this is very, very minor, and in most use cases, it was just fine to work with the MapReduce model. But if you have such examples, I would really like to hear them.
Okay. If there's no more questions, then I would like to go for a break, half-an-hour break. I see no hands, so I say, I see you back in half an hour. Thank you, and thank you, Martin.
Feel free to reach out to me. Yes. Thank you.
Especially with the migraine. Drinks are in the back. It was undetectable that you had a migraine.
Oh, it went through.
Yeah, exactly. Went quite well, I would have to say. It's a very interesting talk. I, of course, personally have never done anything with Spark before. I'm like, hey, okay, now I can really put it a bit into how it fits into the ecosystem. Of course, I have some other things like maybe we'll wait probably have more of an opportunity to discuss it. Yeah, cool. How are you feeling at the moment?
Now, really.
Yeah, better.
Yeah, sometimes it was really shaky, but
It's pretty good.
I'll talk to let you know, soon I will update you how.
Cool. Love to hear about it.
Yeah, it was nice to meet you. To all of you interesting stuff. For me, it was really new and fresh, just learning. So, yeah, thanks. Okay. Bye.
hey.
Good. Yeah, that's awesome. That's why probably it doesn't work.
New Spark on Databricks and working a lot with data frames and also some using times. And I know that at a certain point, if you switch a lot between different representations or rows and case classes, that the JVM uses more memory. What's a good way to tackle it, or to see if it happens?
But I would say, like, why do you switch so much? Maybe, so people tend to use data frames very often because, like, it's just good for certain use cases if you want to do high-level aggregation and stuff like that. But if you have to switch that often, the question is, well, why are you using them in the first place? Maybe you just are better with RDBs.
I guess it's because of the expressiveness. And then most of these case classes, they're domain objects, so that also means we have some extra methods that we could use in some places. And the switching is mostly because I have some domain objects, and then I want to join some other data in it. But joining is really difficult between two sets of domain objects, because joining to a tuple sometimes, in my experience, it doesn't work that well. Joining between joining rows together to get larger objects.
But why is it hard?
To get the right join condition. Mostly, I guess it's mostly because that I need to do a left auto join. That's not possible by just moving objects. Let's say I have two sets of users, and they can have the same email address, and I want to have one set join with the left join. I cannot make too much of those. I'm not sure.
Can you drop me an email with this? I would be really curious to look at it.
Yeah, if I find a concrete example.
Yeah, but generally speaking, like, I would say if, maybe it's too simplistic, but if you end up with writing so many speeches between one model to another, and if you have to find this many UDFs, maybe it would be just easier to go with RDBs.
When do you know that you're running into memory problems because of this performance?
When do I know? When the job fails, and you know that, well, so it's kind of tricky, because I get that quite often, like when I work, especially when I work with analysts who are just pissed that, they have the logic should work, but it doesn't work, and they don't know why. So the UI, but sometimes the UI is shaky as well, so some information disappears. Then make sure you turn on like, if you're running it in Yarn at least, the log collection. So all your data all your logs goes to the same place in each DFS service. You can get an idea from there. And it is likely that when you look at the driver, you get some stupid message like executor lost failure, so you have to go to the executors and look for the root cause. But unfortunately, I don't have any silver bullet for that. You have to just go and look there, and like with some experience, you get some feeling like where to go first and stuff like that. But if you happen to experience that often enable this logs, that should help. And And I'm serious. If you have this example, just send it to me. I'm really looking forward.
Where and how do you usually run your clusters?
Sorry?
Your clusters, like where and how do you run them? Do you have like recommendations? What's good to use?
So I've been always using, but what exactly recommendations?
Yeah, no, like
size of machine.
Do you run it?
Or what?
No, do you run it yourself, or what platforms?
So it's always on premise. I've always worked on premise. Do you have another experience?
No. I've tried Databricks, but just for some course to get in for some Spark introduction MOOC, basically. I don't know how that scales in real life.
Compare Spark to other things. Is it like, you say Spark is a database, or is that
No.
something completely different?
It is for processing, framework for processing data. So you read data, you can connect it to many places like Cassandra or SQL database or like most common is Hadoop. And you process the data from there. So you read the data, you calculate the result, and you write the data back. That's how it works. So common, like very common is that common example is that you basically do all kinds of analysis, you connect your analytics to it, and they perform the queries they used to do in regular database. But the difference is that now they can work on larger data sets and get distributed.
Or they can also work on multiple database instances.
Yes, but so example, my client I worked for, they had like 150 million users, and they were collecting these events, and they had like multiple slaves of MySQL, but at some point you just cannot keep up the replication.
Yeah.
Sorry?
You have Hadoop for before Spark.
Yes, exactly.
I could query, but in Hadoop you could also write the same query.
Yes, you can. Although, first of all, the API is really attached. The libraries I work with are really clumsy, and Spark gives you the caching, which is like a huge advantage if you're doing something more complex. If you are doing iterations, so if you are doing iterations in Hadoop, you would have to build the data all over again.
Okay.
And Spark can use it. Nowadays, Spark gives you like a bunch of tools on top of it. So, like if you want to do graph algorithm, the library for that.
Okay, yeah, it's a lot. So
That's actually when my question about like MapReduce possible algorithms, like when you're looking into graph problems, I think then that's something where you very quickly get to learn, because a lot of things there are inherently sequential, or like at least to some degree.
Yeah. So, but it is still MapReduce. Again, it is just smarter with memory. But it's still MapReduce. So in that terms, like if you're comparing it to MapReduce and by MapReduce, I mean Hadoop, yes, there are huge advantages. But if you're just talking about the programming model, which is still MapReduce in Spark, I have not seen anything which is like really problematic. You can express a lot in MapReduce.
It's quite interesting that you have not. So for the use cases that I currently have to deal with, I'm like thinking, could that even work? Like maybe,
but what kind of use cases do you have in mind?
So I work for a weather forecast company, Meteor Group. And so it's meteorological data, and what we're doing is also like physical simulations. There you're lost anyways, basically, so you can't do that. But we don't do that a lot. We more buy that from government agencies with supercomputers, and then
Thanks, everybody. First off, thanks to Martin for the excellent talk. But now it's time for mine. For the last year, I've had the opportunity to work on this awesome project for the Olympics. I've done that at Gracenode, and I'll be telling you more about it today. So first, something about me. Why should you trust me? I'm a Scala developer and data engineer at Codestar. I've been working here for at least 3 years now. And I've mostly been doing stuff with Kafka. That ranges to managing a cluster at WakeCamp, to doing library integration between Kafka libraries and stuff with logging at the client, as well as doing just regular application development involving Kafka. I tend to like the upsy side of development, so I really like digging into metrics, configuring my logging properly, and that kind of stuff, deployment pipelines, all that jazz. And also, as a small fun fact, I'm not the first of my family to do something relevant for the Olympics. So a small thing about Codestar, I think most of you already know by now, since you've been here for about an hour, or maybe more. We're a small team of passionate developers, and we mostly focus on functional and reactive programming, mostly with Scala and JavaScript as well as TypeScript. And we have awesome clients like Gracenode. And Gracenode is a business-to-business company, mostly focusing on audio, video, automobile, and since somewhat recently also sports, with the most recent acquirement here in Nieuwegein as well as Halifax, Canada. It's a global company. It's all around the world, ranging from the US as well as Mumbai, somewhere in Germany, here in the Netherlands, and Canada as well. And the project we've been working on has been called Olympics Premium. And Olympics Premium is basically a suite of widgets that clients can embed on their website to give a very good and nice overview of what's happening all around the Olympics. And yeah, what do these widgets look like? So what you see here is an overview of the more basic stuff that we've been showing in terms of the medals that have been awarded all during the Olympics, broken down per country, but as well as per athlete. And there's also historical data in there, which is one of the hugest things about Gracenode Sports, is that they just have this enormous database of all the Olympics and other sports events ranging back to whenever. So there's also a nice view on that on the widgets as well. Another nice thing is the schedule widget, in which people can see what events were coming up and when, and give a nice breakdown into digging deeper into these events and like getting the real juicy details, which most of my talk will be about. So you see an example here for biathlon. We gave a very interesting view on what all the intermediate times are for every athlete on every intermediate position. I think you're seeing the 12th kilometer here. Yep. So you see that some people have already passed that point, so they already have an intermediate time. Some other people haven't. You also see nice penalties that people got because they missed some shots during the biathlon event. So another one that is really good is this short track widget, where you see the intermediate times for every athlete, as well as just the number of laps that they still need to get through. A similar one is this one for luge, where people just dive down these slopes on their sleds. You see also the nice breakdown on intermediates, but this one is a bit more interesting still, because we see this information like we have the current athlete here. This is her intermediate times, but also we have the leader that is already finished, of course, and you see the next participant, as well as at the very top how many athletes already completed their run. This is a very rich widget with very live updating data, of which we see a second example here for a speed skating event, where we see a nice breakdown per lap that people are going around the rink, where you see the intermediate times, as well as what people have been doing so far. So we nicely see Irene Wust at the first place here. Yay, Holland. Another nice one is this play-by-play view on ice hockey. So you see in very much detail what the scores have been so far, what penalties have been made by which athlete, as well as what goals have been made and who the athletes were that actually did the assist. Very detailed stuff. We also have player statistics, which is just insane, but too much to show in this on this beamer. A smaller one for player statistics is this one for curling, where you nicely see the statistics for every athlete that is currently throwing his stones. And we even went a bit further than just these widgets that people showed on their websites, because we also had an integration with television, which was just completely awesome. People in the US actually saw this on their television, so that's pretty cool. So how did we achieve building these widgets? One of the biggest boosts in that was the Olympic data feed. The Olympic data feed is, well, let me just show you their own definition. The Olympic data feed is a unique set of messages which can be delivered in real time and contain live sports-related data. They include schedules, start list, results, et cetera, even weather updates, which completely boggled my mind. But basically, the ODF is a set of messages that is being sent by the Olympic committees from every Olympic venue, and they just give all kinds of updates on what's happening during the event. So yeah, what does that look like? We have a DT current file here. Sorry, it's XML, I know. So at the very top, you see this document type. It's DT current, and there's a document code which identifies for what kind of event this is relevant data. So in this case, you see that, I think you can read it. It says SBD for snowboard, and then W for women's, and then it's parallel giant slalom, and then a lot of dashes to make some space for events that might be a bit longer. And then you see that it's the 8th final, and then the 5th heat, and the first run, or something like that. And what you also see is that at this current time, there's these 2 athletes that are currently going down the slopes on the red and blue, with the red and blue bib, like the thing that they're wearing on their jerseys. And we also see which athletes will be coming up next. So this is already kind of cool information that you can get about the event. One other example is this DT result file for SSK for speed skating. Wait, let me just, I got the wrong slide. Anyway. So what we see here is that this is a useful thing to enlarge. So we see this extended infos part, which shows starters 30 and the complete 18. I earlier showed that the progress bar, we built that one using that piece of information. But much more than that, this also shows for every athlete, it shows the results, including intermediate ones and maybe some additional information. I've seen for figure skating, it even contains information about what kind of triple gainer somebody did, and it's just very rich data. But yeah, you get these XML files with data. That doesn't necessarily mean that you already have good widgets. You need to combine these things before you get there. And that's where most of our work will be involved. And I'll be telling you a bit more about our architecture that we use to do that. So coming up with the next slide. In a very basic way, we get the XML from the Olympic venues, which we ingest, put somewhere in storage, process the files, and put them ready for an API to leverage which widgets can pull, and then those widgets will be embedded on a client's website. Sounds kind of straightforward. In essence, it really is. So in the past, Gracenode has been dealing with this in this specific way. When files are received, they are ingested by just dumping them on a single file system and having a file watcher watching those files, picking them up, extracting the relevant fields, and injecting that into a database. Once that is there, in some periodical moments, the data is being replicated over to the calculation database, which then, from a series of database triggers and stored procedures, calculates derivative data, which can then be replicated over to another database, which where it gets denormalized and then it's put ready for the API to use. Yeah, the main problem with this setup was that it was just too slow. It took about 40 seconds for one single file to basically reach an updated piece of information in the API. And previously, 40 seconds might just be okay, but in this day and age, clients want it just to be faster. They want to be faster than social media, for example. It's just, you don't want to get beaten out by just anybody who's on Twitter. And you also just need lower latency to get these rich features, because if you look at that current block that I was showing earlier, where you saw this athlete is currently going down the slopes, you want that to be current. You can't be behind by a minute and then just showing irrelevant data. So we had to change this around a bit, and that's how this setup originated. So we basically split up the flow in what we had been calling classic, which we already saw, and we put a next fast lane, nicely dubbed Bolt by one of my colleagues, for processing the sports files in a super fast way. And then the fast and the slowish API can be combined together in another single API, which can be used by the widgets. And with this separation between fast and classic data for long-term storage and historical data, it also became possible to join in extra data that may not have a direct place within the long-term database. For example, we also were able to now join in relevant data from the Olympic broadcasters about their own video feed. I'll show you more about that later. So I guess you guys can guess it for a bit what this fast pipeline looked like, but I'll show you a diagram. So yeah, instead of putting stuff directly on the file system, we let Kafka put it on its file system. And from that point onwards, we used basically Kafka streams to process these updates, join together data, aggregate stuff, do all kinds of processing, mapping IDs to IDs that were relevant in the Gracenote database, all kinds of stuff. And once that processing has been finished, the data in a pre-processed manner is being put on another Kafka topic, which is then synced to a MongoDB database, which can then be leveraged by a faster API. So yeah, what have we been using to build this architecture? That looks like this. All our infrastructure was running on AWS, and on top of AWS, we were running Kubernetes and Kafka, which was managed by the Gracenote operations team, which was a huge help. I've been operating Kafka clusters earlier, and it's just a lot of work, but luckily this time around I didn't have to bother with that. And on top of Kubernetes, we were running our services basically Docker containers running Scala applications, and those Scala applications were using both Kafka streams as well as reactive Kafka to interact with Kafka. And next to that, we had Camon, which is a great library for creating metrics in your Scala applications. I can really recommend that one. And those metrics were being pushed towards both Graphite for kind of a legacy way of dealing with stuff, and as well as Prometheus, which was also running on Kubernetes. And for extra insights, we also used Instana to get insights into our entire stack, not just the Scala applications. Yeah, so that sounds all pretty cool, but yeah, give us some stats. How was this working? What did we have to deal with? So yeah, Gracenote has about 30-ish businesses that were using this product, and that led to having over 200 million users within those two and a half weeks. And from the ODF, we reached about somewhere between 50 and 150 messages per minute, which is not that much. But we had a nice processing latency from ingestion to being available in our API of about 500 milliseconds, which compared to the 40 seconds that we had before is just a huge improvement. And just for those messages per minute, I also wanted to include the stat that we could go a bit faster. So yeah, a typical day of Olympics looks kind of like this. At about 1 a.m. Dutch time, people started sending out data that the Olympics were in Korea, for whoever doesn't know. So that was a bit of a weird time zone for us. But yeah, they started sending their data at 1 a.m., which just continued until about, what does it say? About 4 o'clock, something like that. And after that, there were no more updates. But Gracenote being a global company, you see that our API had to deal with a constant load of requests, which nicely stays below the, so if you look at the response times, it's the 95th percentile that stayed below 40 milliseconds, and I don't know what happened here, but at some point we just dropped below 20. Maybe we did a good deployment, I don't know. But yeah, I think you guys came here to see some usages of, well, what do you do with Kafka? So I'm going to give you a few examples of those. Right. So like I said earlier, you were using 2 clients basically to interact with Kafka, one of them being Kafka Streams. For those of you that aren't familiar with it, it's a very lightweight library that you can easily integrate with your service. It doesn't require you to have like a proper cluster set up already, like you do need if you want to do Spark streaming. It's super powerful if you want to do stateful operations because it uses Kafka again as a backend to store its state. And it's mostly useful for processing files, getting stuff from Kafka, and inserting updates again back into Kafka. And on the other side, we were using reactive Kafka, which is a Akka Streams library, which leverages Kafka consumers and producers under the hood to build up sources and sinks relevant to Kafka. And we fall back to this library whenever Kafka Streams wasn't that suitable for us. And I'll give you a few examples of that as well. But starting off with a few Kafka Streams ones. So yeah, if you look at this one, which was relevant for, I think it's a snowboarding event. Yeah, Red Gerard was snowboarding. What you see here is an expansion of extra details of what this athlete did during his participation in the snowboarding event. And what you see here, and that's very typical of snowboarding, is that every athlete gets to go down the slopes 3 times and try to get a best score. So that's all the 3 columns that you see here. He did 3 runs, and we nicely showed that thing in one view, which is something that you want as a user of this data. However, the ODF doesn't deliver this information together in one message. It gives you results per run, and that's it. So what you see on the left side is what it would look like for run 1, and on the right side you'd see what it looks like for run 2. So whenever an athlete finishes one of his runs, you get a new update of these files, but it only shows, in run 1, these were all the results for all the athletes that competed in that run, and the same thing for run 2. The only real difference that you see here, besides the scores, is these 2 headers that were on top of the files. And really the only thing that's different there is this bit here, where you see that the 1 and the 2 indicate that these are different runs. And yeah, since these are the keys that we were using in our streams to partition our data, we want to handle the updates per sport event sequentially so that we don't update our state in a wrong order. We had to do something here because these keys weren't leading to the right updates. So what we had to do is basically graphed here in this diagram. You see different colors here for event or updates that basically ended up on a different in a different order, so different runs or units as a more generic term. And what we wanted to do in order to combine these things is to aggregate all our events, or all our, what's the right word, all our messages basically, for all these units. which you see nicely here. The updates are flowing into the results detail parts aggregator, basically. They are stored together in this small bucket, and then once everything is there, you can export a message saying, hey, these are all the relevant pieces of information. This is the full results detail. Yeah, so what does this look like in Kafka Streams code? It's this small bit of code. So given a k stream of results that as keys has these strings, which are these document codes, we want to discard the unit bit of information, basically detailing which run this is. We don't care about the run. We want all the relevant information for everything for that event. So we discard that, and which means that we need to basically repartition our data. So what Kafka Streams will do under the hood here is create an intermediate topic where the rekeyed stuff is being put on. But once that is rekeyed, you can group by that key and then aggregate over it. So in the first line of this aggregate, you see that we have a multi-unit aggregate that is first empty. There's nothing there yet. And the second line there on line 8 shows that once we get a new update, we add it to our aggregate. So if we have more information for run 1, we put it in there. If we have more information for run 2, we put it in there. If we get another update for run 2, we overwrite the previous stuff that we had for run 2, but we keep it together with the one from run 1 still, et cetera, et cetera. And once that's there, we basically map that aggregate to a more richer piece of information, which was that full results detail thing that we saw in the widgets. In a similar vein, but a bit more interesting is this one. I already touched upon it earlier, but you see all kinds of pieces of information here. You see the current participant, you see people, the one that's leading, you see who's coming next, you see the actual results, you see how many people have finished and how many still need to start. So we had this DT current file that said this is the one that the person that's actually current, and this is the person that is next. We can use that bit of information, but we're still not there yet. We need to join this information together with that other result file, and I'm going to use this one, that we also saw, and we can use this one to get that progress bar information via these starters and how many have completed, as well as the intermediate results that are in there. Similarly, there's also messages called DT cumulative results, which are somewhat similar to this one, but give more information about the total score that people have gained over an event. But yeah, we want to join this information together, basically, and that looks like this diagram. So we get updates, we get DT current files, and we get results. We also get cumulative results, which may have the wrong key that we need to rekey. And eventually we want to join all those pieces of information together, and again aggregate over that one and send out an update once we get new information. Kind of similar to what we saw earlier, but now we have multiple pieces of information flowing into our system, or our flow. So in code, it's not much more than what we saw earlier, but yeah, it's slightly different. So in this case, we have multiple K streams, one with the current files in there, one with the results, one with the cumulative results. In the diagram, we saw that we had to rekey the cumulative results, so that's quite easy as well by just selecting a new key. And once we have these 3 streams, we can merge them together, group them by their key, and again aggregate in the same way that we did earlier. And then once we get the aggregate, map the aggregate to the actual piece of information that we want to show in our API. Sorry. Right. So the next one is one of the things that we had to build with additional data that didn't come from the ODF. So that's the information coming from the Olympic broadcasters. You may have spotted it already, but if you haven't, there's these watch buttons here. One of the product people from Gracenode told that this was the best feature that we've been building over the entire year. What this does is if you click on this, it will deep link into the stream of this broadcaster and just jump directly to the part where this athlete will go down the slopes, or is this? Yeah, I think it's alpine skiing. I don't know. Anyway, we had to join together data that actually came from the ODF, the results, but we also had to join this with data coming from a different source entirely. Unfortunately, they are also using the ODF schema just for their headers. It's a bit of a weird example here. Maybe I should have just faked the data and called it like BDF body or something, but yeah. These are different XML files coming from an entirely different source. This isn't coming from the Olympic venues. This is coming from broadcasters that tell us information about, right now on the television, you're seeing that this athlete is now going down the slopes. So there's a start keyword in there, and this is his ID. If like the Queen of England would be there on the television, you would see, oh, the Queen of England is waving. There's all kinds of weird stuff coming along in these in these BDF files. But these are the ones that are relevant for us. We want to know whenever a participant starts, and we want to know at what time he does it, or at least when in the stream this happens. So yeah, given a start keyword and a participant ID that belongs to that, we want to extract the timestamp and put that in a relevant field. So in the diagram, given some of the start list, basically the stuff from ODF that showed all the participants in there, including their results, we want to just aggregate those, but we also want to look at the video logs and filter those until we only have the start keyword ones and extract the start times and aggregate over those. Given a participant, what is his start time? And then join those pieces of information together with the start lists, aggregate over those, and then just output one single file that says, for every athlete in this event, this is his start time. Again, the code doesn't look that different, but yeah, maybe that's one of the powers of Kafka streams. So we have, in this case, a table of start lists. We're aggregating over all these start lists. And we also have the video logs, which is still a stream. We filter these events to look for the start keyword. And once we find one, we want to extract the relevant information for an athlete. Again, group by that, aggregate it, so we get a K table of athlete start events or something. And given that K table of start times and start lists, we want to join those two tables together. And once there's an update on either the start lists or one of the video logs, we want to output a new object that says, hey, this is all the relevant information for a single, well, watch run message, as we've been calling it. So yeah, that's basically it for Kafka streams, I think. Yeah. So then we have an example for reactive Kafka. And the diagram looks a bit different here than what we've been seeing earlier. The interesting bit being here is that as data flows through this flow, we're traversing the network to write to a database instead of Kafka or yeah, well, we're not interacting with Kafka at all there. And that's actually where reactive Kafka became interesting for us, because Kafka Streams doesn't really have a good way of dealing with asynchronous programming as we often do in Scala. As soon as you get a future, you're basically kind of screwed in Kafka Streams. You can await that future, but I don't see anybody shivering, but I just mentioned the word await, so sorry about that. And reactive Kafka actually has a good way of dealing with asynchronous programming. So that's actually why we just grabbed that client, type of client in those cases. So in this case, this was the part where we already had these messages coming from our processor ending up on a new Kafka topic. But those aren't still really queryable by our API. So what we did was we created this application that consumed from that Kafka topic and grabbed all these pre-processed and prepared API calls, grabbed them from Kafka and inserted them in a Mongo database. And from that point onward, it published a new kind of message on a new Kafka topic that detailed this piece of information has changed. And that could then be leveraged by other kinds of consumers, whoever was interested to do other kinds of things with that notification. For example, we could use it to purge our caches for our APIs. as well as push data to our non-API clients. And this is actually super simple to do in reactive Kafka. So you start a source of messages in reactive Kafka by just writing consumer.committable source. And you give it some consumer settings as you normally do with a Kafka consumer. And you tell it which topics to subscribe to. All pretty much straightforward. And from that point onwards, you can do all your mapping, flat mapping, and what have you. Basically anything you can do in Akka streams. And in this case, we have the map async operator, which allows us to do basically asynchronous programming. In this case, we send our update to the database, and then we map that database result to a new message that we can leverage later. So once that future completes, it will be picked up again by the following map operation, and it will then be transformed to an update notification. And once that update notification has been created, it will be written to Kafka again using a Kafka producer, which is in this case a committable sync using some producer settings that tell reactive Kafka which topic it should use to write to and what other kind of configurable properties it has. So yeah, 8 lines of code. Some other thing that isn't really well suitable for Kafka streams is time-based operations. You can do kind of windowing in Kafka streams, but the difficult part is to, like, I want a batch of 5 seconds. That's just not something that Kafka streams supports really well. You can tell it, I want to get all updates that fall within this window, and you get these updates when they're there, but you don't get a full batch after that window has been closed. You need a new message that will actually get a new window. It's kind of awkward to work with, but for good reasons. They have very good blog posts about why this works, but that's not always what you want. So in our case, we had these updates notifications, right? And we can transform those update notifications to basically URLs that need to be purged from our CDN that we've also been using as a cache, basically. But yeah, we basically don't want to DDoS the API that says, please purge this URL, because that URL will probably be the same if you have a live running event. You want to do that in a bit of more controlled manner. So basically, you want to deduplicate URLs over a small period of time, for example, like 5 seconds or something. And that piece of windowing is something that reactive Kafka can actually do quite well, and Kafka Streams just doesn't support. So yeah, you want to do that deduplication, and then still you don't want to just do single requests of please purge this one URL, dear CDN provider. I want to basically purge this set of URLs, so you may want to do some batching before you do your requests to some kind of external API. So that's why there's a batch operator in here as well. And there may also be some rate limits involved that you want to adhere to. And that's also something that is super easy to do in reactive Kafka. The code is a bit more than what we've been seeing previously, but it still fits on a single slide, so I think that's kind of okay. So yeah, given a flow of messages that come into our system, we want to map those messages, or basically we want to group those messages within a specific deduplication batch time. I'll just get rid of this zoom in thing. So you want to group within. We're gonna want to group within that batch time, and then once we have that batch, we want to map over that batch basically by deduplicating all the URLs that are in there. And after we've done that deduplication, we want to again group within a batch with another batch time in there, which may or may not be smaller. And we also may want to limit the maximum size of our batch, depending on what our external API allows. But once we get a new batch, we can transform that one again, as you see here. And then that rate limit that we saw earlier is just a single line here where you say, please throttle this stream with requests per second per, 1 second here. And as messages flow through that part, we can map that batch again to an asynchronous request to our external API that says, please purge this set of URLs. And once that's completed, we can commit back to Kafka that we actually handled all these requests properly. So this seems, well, pretty powerful and, yeah, pretty cool. So, well, that's it for our reactive Kafka examples. So we saw some nice use cases, but you still need to run this in prod, and having good code examples and running stuff properly in prod may be something different. So I want to give some pointers and show some stuff that we've been running into while preparing or actually running our operations. Yeah. So starting with, I'm not going to start with unit test. Do your unit test, please. But integration tests may or may not be a bit difficult. In case of Kafka, it kind of is. But there's good solutions. If you're using Scala test, there's quite a good library called Scala Test Embedded Kafka, which you can use to start up a Kafka cluster in a very controlled manner. It will run embedded within a JVM, and you can really accurately control. I want to publish a message on this topic, and I want to see what comes out at this other one. So that's kind of good. But something that we also used quite often was just this library that you can use to start up Docker containers from Scala. It's called Docker IT Scala from Whisk Labs. It's a project that I've been using quite often, and it's really quite good. But yeah, it allows you to interact with Docker from Scala. And we've been using that to start up Kafka and assorted other dependencies as black boxes. And we could use that to just, well, run our entire application and just fire off new events and see how our application deals with it. So that was really good in terms of integration testing. We also did a load of load testing. And we had two kinds of approaches here. One of them being just simple API load testing, which is not that hard. So we used a tool for that called Vegeta. You can use that to blast away at your API. It's very, very scriptable, so you can easily distribute it over multiple servers. A lot of our colleagues have been writing smaller scripts called Goku and whatever, Saiyan Army, to distribute it over multiple servers. So that's very good for the API load testing. But yeah, testing these Kafka kind of things where data flows into your system and you want to see that the latency is low and you're not accumulating more lag, that becomes a bit more interesting. But in the case of ODF, we're actually kind of in luck because there's a lot of test events actually that go on pre-Olympics in which actual ODF files are generated, and we can just capture all those and like build up a very good suite of test information that we can replay later, which is exactly what we did. We just grabbed together basically all the test events that we could find and just blast that at our ingest service and just see how many files can we ingest until we start accumulating lag on one of our applications. So that's actually how we figured out that it was about 2,000 messages per minute that we got, just without any kind of tweaking. So at that point we thought, well, good job, there's no extra tweaking needed because we're just going to get way less information anyways. But yeah, once you actually do need to start tweaking, we couldn't help ourselves, we still kind of did it. We noticed that it's a bit hard to really make your application really optimal for your workload, at least in this version of Kafka Streams, because the way Kafka Streams distributes its work is it acknowledges this concept of a task. Basically, grab this message from Kafka, transform it, and write it back to Kafka again. Those tasks are all considered equally as costly and are just distributed randomly over all your applications within your Kafka Streams cluster. But yeah, these tasks typically aren't equally as costly. Grabbing these huge XML files and parsing them and grabbing out relevant information is way more costly than just grabbing a single key from one of your Scala objects and returning that. So that's a bit weird, and that can lead to one of your instances by random chance getting all the tasks that are super difficult and take a lot of load, and then another instance within your cluster getting basically nothing to do. Luckily, there's a fix planned for 1.2.0, so I'm looking forward to seeing that. I think it'll still be a while, but at least they're working on it. Yeah, and for similar reasons, it's a bit hard to accurately do capacity planning, but because, for example, that task assignment that we saw earlier it's built up on deployment time, your application startup, and this work is distributed over your instances. But the way that those partitions are assigned is more like a hint to your cluster. Please try to align yourselves in this way, but there's no like guarantee that your cluster will actually will distribute their load in that way. So it's a bit of like you need to retry and retry and retry. And if you try enough times, you will probably find like a good average on what kind of capacity you need. But yeah, these estimates aren't like, you can't do it within 5 seconds. You need to start up your application, start producing a lot of files, and maybe let it run for about half an hour. And that will give you just one single data point. And if you want to do that very often, it's just not that workable. They do have very good documentation, though, about what kind of things you need to think about, your buffer sizes, your number of partitions, stateful operations that you're doing. All that kind of stuff is, yeah, they're giving quite a few good examples in there. Yeah. So one other thing that we ran into is that error handling, it is important, and there's basically almost no support for it in Kafka streams. What they want you to do is wrap everything in a try-catch block and do your error handling in whatever way fits your needs. But yeah, that requires some kind of like diligent work from your developers. And although we try our best, we may fail to do it properly sometimes, which can lead to poison pills in your Kafka Streams application, which is a very bad thing. So being able to skip over these messages may prove very useful. And we've actually used this in production, I think, a few times, sadly. But yeah, nowadays, I think since Kafka 0.11, there's a very good command line tool to reset your offsets. And you can use that to skip a single message or something. So that's, or just skip everything that you've been building up in terms of queues or lag. But yeah, that's kind of useful. Again, reactive Kafka was actually a bit better in terms of error handling. Echo Streams has quite a few good ways to deal with errors. You can skip messages and that kind of stuff. But one thing we actually did run into is that there's a very good piece of documentation, or maybe it's not good at all. On the Reactive Kafka website, they tell you, they give an example of how you should restart your application once you run into failures. And that kind of works most of the time, but sometimes, and I think this is just a bug in the Reactive Kafka library, but sometimes when we ran into an issue, our application tried to restart, and what Kafka consumers typically do when they restart is that they, well, reassign the work that they've been doing. And what happened was that partitions did get assigned to our consumers, but for some reason they just didn't consume from those topics anymore. And that was really kind of awkward because, yeah, you want to keep consuming from your partitions. Anyway, what we eventually did was just, we didn't do anything related to that restart behavior that they advise on the Reactive Kafka documentation. And what we did was just let the application crash and let our supervisor, in this case Kubernetes, to just restart our application. And when it just booted up from scratch, everything went just fine. So yeah, the nice piece of documentation about error handling has been linked there. I'll probably share these slides afterwards. And there's also plenty of GitHub issues with like these partitions that get stuck. There's plenty of issues on the Reactive Kafka library that are being mentioned, and I expect that it will be fixed sometime soon. But yeah, be aware of that. It's a thing. And I don't think I can mention it often enough, but please monitor your offsets. Yeah, I think that's about it. So we saw today a few examples of how Kafka streams can help with your stream processing, especially when you're doing stateful operations. But in some cases, you want to resolve back to reactive Kafka, which can help out when you're doing asynchronous programming or time-based operations or yeah, that kind of stuff. And I also gave some nice examples of how to prepare for your to run your stuff in prod. And I guess that's it. So if anybody has any questions, I'll be happy to answer them.
Yes, applause. Yay. Any questions so far? If not, I do have a question for you because you alluded to it in the beginning, but you said someone else in your family has also done something at the Olympics.
Right,
and
yeah.
you just left it hanging there.
Yeah, so my dad competed in the 88 Olympics in Seoul. So we both were somehow involved.
Almost the same thing,
in,
right?
in a South Korea Olympic event.
And he was...
He was also 27.
Yeah, but it was like, it's like you were working with streams and he was working with streams.
Yeah, he was a sailor.
Yeah, he was a sailor. Okay, good. Anyway.
That's a good one.
That's my joke for today. Okay, so any other questions so far? Yeah.
So you mentioned the XML and the skew problem. So I understand that processing huge XML is harder than processing small events. But you also mentioned that those XMLs get distributed randomly. So I don't get how it's a problem and what would be the solution for that.
I'm not sure if I said that files were distributed randomly, because we actually had a very strict way of dealing with how events were published in our case, because basically what the ODF was sending out is, this is the full new state of this event, and we actually want to process those messages sequentially, because we don't want to have like an update for timestamp 10 to proceed a message from timestamp 9, for example. So we actually wanted to process those messages in order. So the distribution of our messages was actually fixed and not random.
And one more, Kubernetes.
Yeah.
Can you just tell us a bit more, like any conclusions from running it, any problems?
Worked pretty nicely, actually. Yeah, I was really happy with it. Yeah, maybe somebody else, Hamza, it worked really fine, right?
The UI provided with Kubernetes is a bit lacking.
Yeah.
It doesn't have auto refresh, so if you want to monitor, you better have a good monitoring solution on the side. Also, yeah, we had to create a lot of tooling on the side for like live logs and stuff like that for tailing instances. I'd say they could improve that aspect.
Yeah, but in terms of keeping our stuff running, it was actually really, really good.
Yeah, we didn't have really any issues for running stuff, except when we run out of memory. It's really hard to figure out that a pod was killed from lack of memory. You had to dig really deep. It's like a basic thing, but that's not something obvious when you work with Kubernetes.
Yeah, I've seen a lot of blog posts nowadays that actually give a detailed description of how you debug that one. Yeah.
Thanks.
Sure.
So actually, I want to point out that we have other colleagues here that worked on the same project.
Yeah. So Hamza was there and Mikhail was there.
Mikhail's there. Yeah.
I'm not seeing Mozart. I
No,
also see other colleagues from Gracenode. So
yeah.
Thanks for coming, guys.
Yeah. Some other questions, maybe so far? No, not really. Do you have a picture of the command center that you were in at night? You have it lying around.
I could dig that one.
Because
yeah,
you were actually one of the people who were sitting there in the middle of the night when the Olympics were going on.
Let me look that one up.
These are, of course, the most interesting things for us to see, right? The most visual thing. Yeah, is it allowed to show it? We get in trouble. They are here, so.
I'll put it up on the screen later.
Yeah, sure,
I'll try looking for it. I don't think it's on my laptop. Yeah, it's in Slack,
okay,
definitely.
Yeah.
But
if there's any other questions, No questions. Then I would like to thank you very much one more time.
welcome.
And also Martin, thank you very much. And there's still some time for drinks if you want. So and to hang around, of course, to speak with our speakers. Thank you. Thank you all.